Now I discuss Einstein's theory of Brownian motion. First, I talk about something called the free Brownian motion. It's described by this Langevin equation, but it's simply the Langevin equation without the external force. So we only have this resistance and the random force. Okay, so now let's recall that in usual ordinary differential equation like this, where ft is some arbitrary fixed function, you can easily write down the general solution, which is this. And t naught is the time at which you give the initial condition, and this vt naught is the initial value. And you see that in this case with dumping, gamma is positive. Okay, when gamma is positive, the system quickly forgets its initial condition. Okay, so because here you have dumping, so we fix t and let this time t naught go to minus infinity. So you give the initial condition in very, very fast, and then this term vanish, and you get this solution. Okay, so this is the solution after quite a long time. And now we can formally use this result to this. So now you regard this psi t as this arbitrary function, and then you can write down the solution of 1 like this formally. Okay. Actually, I remarked that our treatment here is not mathematically rigorous, but you can make everything rigorous, and the results are all correct and rigorous. Okay. And what we present is a standard physics treatment. Okay, anyway, we have this formal solution of the free Brownian motion. This is a formal solution. So by using this, I first compute correlation function of v, the velocity. Okay, and you simply take the average expectation value of all this, and only this part is random, so you get this, but this is 0, so you get 0. Of course, in average, v is 0. We are after quite a long time. Okay, and now I compute this correlation function of v at 2 times t and t prime, and of course you simply multiply these together, so you get this double integral, and here you have this correlation function, which we know to be given by this, so we get this delta function here. And here we have to be careful about the order of t prime when we perform this delta function integral. So here I assume that t prime is not less than t. And then if you integrate s prime, you always pick up a point at which inside here becomes 0, inside delta becomes 0. So you always pick up delta function by first integrating over s prime. If you try to integrate over s, you're in trouble. Okay, so this order is very, very important, and you can perform the integration of delta function, and you get this. And then you perform this integral, and you get this. Okay, and now we have this inequality. So this guy here is non-negative. So this shows that this correlation function decays. Here, if you set t equal t prime, then we get the expectation value of v squared. And from this, and it's given by this. So from this, we see that the expectation value of the kinetic energy is given by this, which is precisely 1/2 kBt, which is the expectation value of the kinetic energy that you expect in the equilibrium state. Okay, and since we have waited for quite a long time, of course, this must coincide with the equilibrium value. So this shows that our theory is okay. And probably you don't remember, or do you remember? Back in page 7, yes, back in page 7, we have chosen this constant a. And before that, from the requirement that we have continuum limit, we have the limit where epsilon and delta go to 0. Then from the existence of the limit, we could conclude that a is constant times epsilon over delta squared. But we didn't know the constant, and here we assumed this form. And gamma turned out to be the coefficient for resistance. M is, of course, mass. And beta is, of course, the inverse temperature. But at this moment, we were not justified to make this choice. And finally, now we see that our choice was consistent with physics, consistent with equilibrium statistical mechanics. So now we know that our theory is consistent and okay. Okay, so this was an important calculation. Now let's compute the expectation value of this displacement. First of all, this is a displacement of x between from 0 to t, and of course it's given by this integral. So if you take this average, then of course it gives you 0, but it doesn't mean anything. Starting from 0, and you may go to right or you may go to left. So in average, it's 0. And in this kind of case, if you want to know the actual value of displacement, of course, you square this first and take the expectation value. Okay, and again, from this expression, you have this double integral, and here we already know this correlation function, but you have to be careful about the order of s and s prime. So here, what you want, an easy trick is that you first note that S and S prime are identical. So and we are here integrating over this square region, right? But if you split into two, then this region and this region gives exactly the same integral. So here we change the integration. So S is integrated from 0 to t, but S prime is integrated from S to t. This means that we integrate in this region here. And so, as I said, these two regions give exactly the same thing. So we have factor 2 here. And now S prime is always not less than S. So here you can use our previous result, and we have this. Okay. Now the hard part is over, and we only need to perform this integral. But it's always not easy to. Well, this is easy, but you have to be careful. And after a careful calculation, I hope this is okay, you get this. And you first of all observe that there is a term which is proportional to t, and this is an innocent part. This quickly goes to 0. Okay, and you see that now this displacement squared average is basically proportional to t. It means that it shows the diffusive behavior that I discussed in the beginning of this part 5. Okay, displacement squared is proportional to t, and usually this proportionality constant is written like this, 2d, where d is known as the diffusion constant. Okay, so here in this case, this is the definition of diffusion constant, yes, and from this, we see that this diffusion constant is given by 1 over beta gamma. Okay. So that's basically all the calculation we want to do for this free Brownian motion. Now we consider Brownian motion under a constant force. So this is really non-equilibrium physics, right? Now we apply a constant force to this Brownian particle. It could be gravity or electric force or whatever. Okay, and we want to discuss this Langevin equation, but it's actually very simple. If you introduce this new variable u as v minus f over gamma, you easily find that this is written in this form. This is nothing but the Langevin equation for a free Brownian motion. So it's very simple, and we can compute many things. But here we only need to compute this simple expectation value. Expectation value of u is vanishing. And then we know that the expectation value of v is given by f over gamma. Let's rewrite f over gamma like as mu times f, where mu is called the mobility. And in this case, mobility is given by 1 over gamma. Okay, mobility means this is actually a response coefficient or transport coefficient, like what we did in the discussion of linear response theory in part 4. We are applying external force and forcing and inducing the current in this Brownian motion. And then this velocity, the current, is given by this force times a constant. Okay, and so this constant is something important. This is a response coefficient. And here's the Einstein's relation. So you recall that this gamma is related to d. Okay, so this is previous page. You recall that this gamma is related to d like in this way. So since mu is 1 over gamma, we conclude that mu equals beta times d, or you can rewrite it like this. And if you recall the definition of the diffusion constant, I think you have already seen this. If you recall the definition of the diffusion constant, this has precise form of linear response relations that we discussed in part 4, page 12. Okay, so shall we take a look at part 4? We don't need to, but actually my handwriting is very bad here. But anyway, so this is we applied something non-equilibrium, like non-equilibrium force or temperature difference. Okay, and this is the expectation value of the current. And here this says that this expectation value of current is given by this yes, f or something, some small epsilon times this here. But this is fluctuation or integration of correlation. And actually, I didn't have to look at part 4. So this is the same equation. I changed the variable a little bit, but this is the same equation as equation 1 in part 4. And you see that these are exactly the same. Okay, the formula looks the same, but also the meaning is the same. Here, you applied external force to the system, and you generated the flow. You generated non-zero flow, and you looked at this coefficient for this transport coefficient, and it's given by this time integral or the fluctuation. So this is a prototype of linear response relation or fluctuation response relation or the fluctuation dissipation relation. Okay, so this was Einstein's theory, and you have seen, I think you are convinced that Einstein had basic philosophy of non-equilibrium physics, especially linear response relation. Okay, so yeah, I had to emphasize that this correlation function is estimated in the system without f. This is for the correlation function for free random walk, free Brownian motion. That is the important part. And this is the transport coefficient that you obtained in this Brownian motion under constant force. Okay, so this is Einstein's relation. But what did Einstein do with this relation? One purpose of Einstein was to count the number of molecules by observing the Brownian motion. And actually, at this time, it was 1905. At this time, there was still an argument about the existence of molecules and atoms. And one argument was that you can never count the number of molecules because you cannot see them. But Einstein showed one way of counting the number of molecules. And okay, so this is Einstein's relation. KB is the Boltzmann constant, but we can write it like this. This is R is the gas constant, and A is the Avogadro's constant. And this tells you the number of molecules. Okay, and now this mu is mobility, but Einstein pointed out that if this Brownian particle is large enough, you can use the result from fluid dynamics. And this is something called Stokes' law. And this mu is written like 1/6 pi eta times A. Eta is the viscosity of water, and A is the radius of this small Brownian particle. Okay. Now, by using this, we can rewrite this Einstein relation like this. And I will examine the character of each quantity here. Okay, 6 is 1, 2, 3, 4, 5, 6. You know what 6 is. Pi, of course, you know what pi is, 3.14. And okay, now R, what is R? This is a physical constant. It's a gas constant, so you know it. You can determine this by performing thermodynamic experiments. T, also, this is a thermodynamic quantity you can measure. Eta, this is a fluid dynamical quantity, but you can measure this by performing a fluid dynamics experiment. So this means that this RT eta can be determined by macroscopic experiments. Okay. Now, what about D and A? Okay, D is the diffusion constant. So then you have to observe Brownian motion, but that is possible. Okay, you have to use microscope, but actually I have shown you in the movie, and you can measure this D. And A, again, you have to use a microscope, but you can measure this. Okay, so these quantities can be measured by a microscope, and this is a very unbalanced in identity equality here. we have the number of molecules. You can never count them in usual way. So this is a very, very microscopic quantity. So the miracle of Einstein's relation is that you can solve this for NA. And you can determine NA by only using 6 pi and these quantities from macroscopic experiment and these quantity that you can measure by using a microscope. Okay, so let's try this. So this is the experimental data that I showed you in the beginning. So from this slope, we can estimate the diffusion constant like this. This comes from the fact that we are in this is sort of two-dimensional calculation. And so I just read off the number. I was not very careful, but anyway, this is D. And A, in this case, A, well, I was told that it was 0.5 micrometer. And now it's very easy to have plastic beads with exactly the same diameter and or radius. And this is one of the advantages of modern experiment. And this is a gas constant, this is a temperature, and eta, you can look up this. This is the viscosity of water. So if you just plug in everything here, and you get this number of Avogadro's constant. And of course, the actual value is 6 point something times 10 to the 23rd. So of course, it's not exactly the same. But look, from this kind of very rough experiment, we get the correct order and more or less correct value here. So this shows you that by observing this kind of Brownian motion, you can really count the number of molecules. And actually, after Einstein's proposal of this theory, French experimentalist named Perrin, I don't know the correct pronunciation, he performed a beautiful experiment and he confirmed the Einstein theory. And we hear that after Perrin's experiment, almost everybody was convinced that molecules and atoms do exist. Okay, so as I repeat, one of Einstein's main purpose of developing his theory was to count the number of molecules and finish this argument about the existence of molecules and atoms. And for this purpose, what he has done was to say open the door of new theory of non-equilibrium statistical mechanics. As I said, in this simple equation, he already had the basic philosophy of linear response relation or fluctuation response relation. Okay, so we have come back to 1905, and my incomplete references are very incomplete here. So let me continue. So we consider detail balance condition in the beginning, but then actually I still don't know who was the first to point out this kind of relation coming from fluctuation theorem type consideration. But I think in this paper by Christian and Carler, they have explicitly this relation. And Einstein's theory of Brownian motion was, of course, developed by Einstein in 1905. It was published in 1905. And as you know, 1905 was a miracle year for Einstein, and he published the paper for special relativity, and also he published the paper about about quantization of light. And that was the first paper of real quantum physics. So it was really a miraculous year. And in this paper, he sort of finished the argument about the existence of atoms and molecules, and he also opened a new field of non-equilibrium statistical physics. And I discussed the topics like the Langevin equation or the Cramer's equation. I didn't say, but there's something called Fokker-Planck equation. These are all very standard and discussed in many standard textbooks in non-equilibrium physics. And I encourage you to refer to these standard textbooks. And this is my message for you who are starting to read these standard textbooks. So this is what I feel. Many textbooks on non-equilibrium statistical mechanics start by talking about the Langevin equation. They really start from Langevin equation. And they talk about it as if it is something you understand intuitively and easy. But actually, for me, it was never easy. I never understood this quickly. So, and actually, probably I said this before, but for me, fluctuation theorem is much easier to understand than the Langevin equation. Fluctuation relation for Hamiltonian mechanics comes only from Hamiltonian mechanics, Lewis theorem, and equilibrium statistical mechanics, and you can derive it very easily. So that's what I did in the beginning of part 5, right? And from this, we wrote down the condition for transition probability, and we guessed the most natural simple form of transition probability. From this, we got Cramer's equation. From the Cramer's equation, we have the Langevin equation, and I'm convinced that this is a good equation. So now you and I can read these books with confidence. Okay, so that was all what I wanted to say in this modern introduction to non-equilibrium statistical mechanics. And of course, I can keep on talking about non-equilibrium physics, but that will be just endless. So I'd like to stop here. Thank you very much for watching. Goodbye.